Okay, so I'm gonna give an extension on this lab, Mambo, but please don't give up. This is all the fun. This is where whatever we studied is going to come together. And I promise you that it will it will take time. It's not straightforward. If you try to migrate all the equations that you have studied, all the control theory that you have studied onto a practical platform, it will be hard, but eventually you will get it. So please don't give up. And actually, I was a smart student came to me and said, hey, it's only just 2 points, might as well I will skip it, so it won't affect my grade a lot. That is true. This project is not a whole lot of points, but the practical experience that you will gain by playing with the hardware, that is enormous. So it's a priceless experience. So please work on the hardware. And today what I would do is I would kind of give you some more hints on how to get that system working. uh, so, and some of you may, there is something else that I want to tell you that I kind of did not discuss in detail. Uh, there is something called as moving average. If you see the output from your roll and pitch is going to be noisy. So there is a moving average block inside the Simulink. What would that moving average do? That moving average would actually do a low pass filtering on your output and give you some signals that are sort of uh, constant. So that actually would make your life a little bit easy. So in last class and in next few classes, we are going to talk about the low level controller. Then we are going to talk about how this low level controller is implemented on the actual hardware, and try to use all this information for the actual control of Mambo. Now, in the last class, we talked about the model simplification. Then one thing that we talked about is how do we achieve the translation of Mambo or a quadcopter. Since it's an under-actuated system, you would have to either pitch it or roll it to achieve the translation in the respective direction. So for an example, if you want your Mambo to go in the positive X direction, you would want to pitch it down and then it will go forward. If you want your Mambo to go backward in the negative X direction, you would want to pitch it up and then it has to go back. So essentially, what I'm trying to say here, and please understand, if you just want to achieve the pure translation, you can just provide the command for a non-zero value of positive pitch or non-zero value of positive roll, and you would achieve the lateral motion of the Mambo. That is how the equations work out. But one thing what you want to maintain is, please understand that you have that yaw coupling that is appearing in the equation for Px and Py. So you want to make sure that your yaw coupling is 0. In other words, your yaw value, the Mambo, should not be turning. If the Mambo is turning, and if you allow or if you make a non-zero pitch or non-zero roll, then you are going to have a very complicated dynamics. So it will not be a pure translation in X or pure translation in Y. So somehow you need to maintain the value of heading, which is psi, to be 0, and then you have to either pitch it or roll it, and that would achieve the lateral motion. Now, in last class, I talked about this, and then I just want to tell you that there is no something called as the negative PWM. So what you want to do is, when you want to pitch it forward or pitch it backward, then you change the velocities of those appropriate rotors, and that will achieve the mambo moving forward or moving backward. So at the end of the day, please understand, no matter what you do, the only thing you can control is the speed of those individual motors, and somehow you should achieve the right value of speed no matter what you do, whether you do experiments, whether you do theoretical modeling, or whether you do some combination of experiment and theory. At the end of the day, the motor speeds is all that you have to achieve the stability. And believe it or not, these small teeny tiny quadcopters that you can buy for $10, they do flips and all, they don't have any sophisticated control surfaces. Only thing that they have is the speed of speed control of the motor. However, there is something else I just want to tell you. Whenever you want accurate speed control, your innermost loop, which is the motor controller loop, needs to run at 10 times higher bandwidth than the outer loop. What does that mean? So for an example, and this is what we will discuss a little bit later today. Say what you want is, you want a hover control, but at the same time, you want it to maintain certain value of Z. How would you maintain a certain value of Z? You have two sensors. You have an ultrasonic sensor that is going to give you the distance from the horizontal surface, and you also have the pressure sensor that is going to give you the pressure. Out of these, which one would you trust more? Now, clearly, when you have an ultrasonic sensor, it actually detects based on the reflected wave. So if you have maybe a desk, or if you have some type of an obstacle, and if your quadcopter flies over that obstacle, the momentary value of Z will be different. So you should be trusting your pressure sensor values more. But then clearly the pressure sensor values are going to be different depending upon where you are on the earth. So for that, what we do is we do some type of a calibration. So we set up the mambo at the ground level, we get the value of pressure, and then we raise it, we measure the pressure, and then we find out the difference in the pressure and relate that pressure difference to change in the altitude. But many a times what happens is, the pressure sensors, the pressure is also dependent on environmental conditions. For example, temperature. So what you want to do is, you want to make sure that the pressure measurement that you get is compensated for temperature as well. For the indoor experiments, what we are doing, we are in pretty controlled temperature environment, so it's going to be fine. But I want you to keep this in mind as we migrate on to coding, or as we develop the control algorithms. So in last class, I kind of talked about what is the low level logic for forward motion, left and right motion. Now let me talk about the logic for up and down motion in little bit detail. This is going to be our next task. So once you got your controller stabilizing in hover, what we want to do is, we want it to hover at fixed Z. So how do we find out fixed Z? So if you think about Mambo, so you have this Mambo drone, and this Mambo drone has a pressure sensor and it has an ultrasonic sensor. And in today's class, we will try to get the data from the pressure sensor and we'll try to get the data from the ultrasonic sensor. So pressure sensor data would be indication of altitude. You also have accelerometer in the Z direction. So AZ. However, please try to understand the acceleration in the Z direction is very, very noisy. So if you decide to integrate the acceleration, the estimate that you are going to get on the pressure, estimate that you are going to get on the altitude is going to be super noisy. So you can't trust the acceleration in Z direction. But you have ultrasonic sensor and that will give you the distance. But the question about this distance is whether your Mambo is here or whether your Mambo encounters a step, the distance that is given by ultrasonic sensor is going to be unreliable. So what you want to do is you want to come up with some type of an algorithm that would fuse the pressure sensor and ultrasonic sensor. So what type of algorithm would you use for fusing pressure sensor and ultrasonic sensor? And this is where the state flow would come in, but we will just, let me give you the basic algorithm. Imagine we want the Mambo to hover at stable distance D. So we want our Mambo to hover at stable distance D. What I'm going to do is I'm going to get the value of pressure. I'm going to get the value of ultrasonic sensor. I would see what should be the relative weights on the pressure value and what should be the relative weight on the ultrasonic sensor value. So what I would do is I would find out the height from the pressure sensor. I would find height from ultrasonic sensor, and then I would use a complementary filter W1 H pressure plus W1 H ultrasonic. However, as soon as I have a translation command in X or in Y direction, I'm to control the height, I'm gonna focus more on this pressure sensor. So basically what I would do is I would set W1 to 1 and W2 to 0. W1 to 1, W2 to 0. So this is the algorithm that you want to use if you want to have a stable hover at a particular location. Everyone understood this? Now, next part is, this is just the mathematical expressions and their simplification. So please try to understand. These are the actual mathematical equations that we are looking at. Now, these mathematical equations, these equations are nonlinear equations that are valid over the entire flight region. But what I'm going to do is I'm going to divide this region into teeny tiny small steps. I'm going to divide this region in teeny tiny small steps. And at each step, I'm going to do multiple samples. So think about it, like at each steps, I'm performing the same calculation 100 times. So what that means, for each time step, for each sample, I can use the linear approximation, which is shown on the right hand side. So this linear model works. This linear model actually works is because even though your original model is non-linear, you are working with a discrete system. You are updating at 100 hertz, which means 100 times a second you are getting data. In other words, sometimes you are measuring the same quantity, maybe 1,000 times, 2,000 times, 3,000 times. That's why what you can do is your linear model would also work when you have very high sampling rate. However, this linear model would fail if you want your Mambo to do the flips, or if you want it to do sort of a very fast maneuvers, because at that time the update rate what you have will no longer be able to linearize the model that you have. And at that time you have two options: either you update the update rate, which means you need a better processor, or you need to overclock the processor. It's possible. Or what you do is you come up with a non-linear type of controller, some type of algorithm that would work over the larger region. Alternatively, there is a very nice algorithm which is called as the gain scheduling. What do you mean by gain scheduling? For an example, we have decided some proportional control, some derivative control, and maybe some integral control for small region of the flight. It works well for the small region, but as soon as the quadcopter goes from this region to the next region, you schedule the gains, which means you change the gains. So your proportional gain would be different, your derivative gain would be different, your integral gain would be different, and that is called as gain scheduling. So finally you are still dealing with the linear control, but those coefficients are different depending upon the flight envelope. And again, there are additional complications that arise when you use gain scheduling. Like how do you switch? What is the switching algorithm? And then you can actually decide switching based on some sensor values, some parameter values, or basically the maneuver that quadcopter is going to do. But at the end, what we are dealing with is we are trying to come up with some sort of linear model, and we are running that in a discrete domain. And since our update rate is very high, that linear approximation most likely is going to give us good results. Now, next point which I want to talk about, is concept of set point control. And then we will talk about the trajectory control. Okay, good. So what do I mean? What do I mean by set point control and trajectory control? So the idea is, so think about set point. Set point is like your thermostat. So you want the temperature to be 80 degrees. You want your temperature to be 70 degrees. You set that point, and then your controller will try to maintain that set point. So in other words, you want your quadcopter to go from point A to point B. You specify point B, and it stays at point B. So you are not controlling going from A to B. You are controlling the quadcopter is staying at A, and then you are controlling quadcopter staying at B. That is the set point control. So mathematically, what this is written as is the position of the quadcopter minus the position, desired position approaching beta, which is the 0th position and some teeny tiny disturbance, So basically what it means is the quadcopter is staying close to point A or staying close to point B. Now let's try to approximate something like this. We want to go from point A to point B, but in between point A and point B, there are maybe a million points. And what I want to do is, I want that quadcopter to go slowly from first point A to the first point, to the second point, to the third point, fourth point. If this motion is quasi-static, which means the quadcopter is going very, very slowly from point A to point B, clearly the algorithm for set point control can be used for maybe some sort of trajectory planning or trajectory tracking. But if your quadcopter is going to have some finite speed, if you want it to go from point A to point B at certain speed, then what you want to do is you want to do something called as the trajectory control, which means you have basically a trajectory. You want it to go from point A to point B, and then you want to specify certain trajectory for the quadcopter, and then your aim is the error between the desired trajectory and the error and the actual trajectory is small. That is what is written by that time dependent trajectory, that equation. In path following, what you want to do is you want to provide a certain path. Say for an example, that quadcopter is going to do a circular motion. This is the path that quadcopter has to follow. So understand that you have a path that is dependent on some type of a parameter, maybe equation of sine or equation of circle. And then what you want to do is you want to make sure that at every time the position that is obtained by that path equation and the position actually reached by the quadcopter is within some norm. It's not the difference at one point, it's not difference at few points, it's the cumulative error over all the points. So that is what is meant by the error in path following. Now, if you look at the controller algorithms that we are talking about, they are based on Euler angles. What it means is if we are successful, even then our quadcopter may not be able to do flips. Our quadcopter may not be able to do AD flips. Our quadcopter may not be able to do a backward circle or inverted circle. Because please try to understand, Euler angles, they lose their accuracy as the pitch angle goes to 90 degrees. So for an example, if you have a quadcopter, if it is going to do a flip in the roll direction, pure roll, that's totally fine, that your Euler angle approximation would work. But if you are going to do a cross flip where you have the coupling between the roll and the pitch, and pitch angle is going maybe like 60-65 degrees, your controller algorithm will not work. Nothing wrong with the algorithm, but the altitude and attitudes that you are going to estimate based on these angles are not going to be accurate. That's why you would have to actually use either the Cottonian or the rotation matrices. MATLAB can do both. As a matter of fact, you can implement the Cottonian based implementation inside Mambo, and Tello already implements the Cottonian based implementation. So this is the simple equation for the PID control for what we are trying to achieve. Please understand, we have a desired theta, and what we have is we have the proportional gain, we have the velocities, and then we have the derivative gain. And in this case, basically, we don't have an integral equation, but what you can do is you can just use proportional and derivative gains, and you will be able to set the controller. Now, next thing which I want to talk about is there are different ways to set up PIDs, and I'll tell you, I will show you how the PIDs are set up in Mambo. Basically, they are set up in a slightly different way. So there is a conventional way of setting the PIDs, and there is sort of the actual coding ways of setting up the PIDs. So basically, think about PIDs as you have the proportional, derivative, integral. Usually we don't use integral. We use integral only when we need to have a very close set point control. But we usually go with proportional and derivative control. So this is the controller equation for the z distance, or basically the forces in the z direction, or the height that you want to maintain. So if you want to maintain the height, then you have this altitude channel. P dot z is equal to velocity that you get from accelerometer, and then you have the vz dot is equal to g. F is nothing but the thrust from the prop, and m is the mass of the quadcopter. And this equation, once we got our hover control or the mambo pendulum working, this is what we would focus on implementing. So with that, what I want to do is I want to actually go to the mambo and kind of show you how you would be able to implement the control. So before I actually start demonstration, any particular question about, so complementary filter, everyone able to get the complementary filter working? My online students, in-person students, did everyone get complementary filter working? Okay. Now, were you able to get the motor working? So were you able to get the motor control the way I showed in the last class? For some reason, my mouse is not working. Let me see. Okay. So what I want to do now is I want to actually go to Simulink. And let's open the code that we started in last class. Okay. So this is motor one. Can everyone see my screen? Let me share my screen. Okay. So what I want you to do is I want you to go here, and this is what we did in last class. So this is motor one, motor two, motor three, and motor four. Now, what I asked you to do is use your complementary filter code from here and use that complementary filter code to control the speed of the motor. Now, what I want to do now is basically try to get this altitude data and the pressure data and see how can we use this altitude and pressure data for controlling the height. So what I'm going to do is, first and foremost, I'm going to go to simulation, go to library browser, and then I'm going to go to the scope, grab one scope, grab one more scope, and you can actually add this scope to altitude, and then you can add this scope to pressure. And then open your Mambos, link Mambo to your computer. Connect using access point. And once okay, so once it is connected, then go to hardware and then do monitor and tune. It will actually run. So your Mambo should be, and then you can actually prepare and take off. You should click on so can you see that the altitude, let me see, did I pull the pressure? Yeah. Yeah, pressure. Now please note, this is the motor control. So you have the data from the altitude and you have the data from the pressure. So now what I'm going to do is, I'm going to put it over here. Can you see the pressure value kind of change? And now I'm going to move it over here. You can actually zoom in. Move it over here. Zoom out. So as you can see, this value changes, and clearly the pressure value that you are getting is kind of noisy. So what you want to do is you want to run this pressure value through a low pass filtering, And the easiest way to do that, so you got your moving average working, right? Finally. So for that, you want to go to moving average. So can you see moving average? So grab this. Grab this block. Take it to Simulink. Grab this block. Moving average is sort of a low pass filtering. Now what I want you to do is I want you to observe. I'm gonna feed the pressure data through moving average. And I'm gonna send altitude data through moving average. If you double click on moving average, it shows you the window length. And there is a difference between the different types of windows that you can use. Now, everyone here is familiar with window. So you have the data coming in. What it will do is it will basically take the first four values, find the average, slide the window, find the next four values, find the average, slide next four values, find the average. So you can actually increase. So, okay, let me say 4. Okay. And what you can do is you can do monitor and tune. Now the question is, what is the right value of moving average? Now, if the moving average window is too big, then what would happen is you lose the dynamics. So it will be sort of a very low pass filtering. But if moving average filter is too small, then clearly your signal is not going to be smooth. And let's do this experiment and I'll show you what happens. So start. Now let's look at the pressure data. Last time you saw how noisy the pressure data was. So what you can do is basically you can zoom in and you'll notice that data is fairly stable. Zoom out. Oh. So you will see that data is fairly stable. So the noise will be minimized. And here, I'll show you. Yeah. Are you with me so far? I'll check this out. I'm going to move it over here. I want you to observe that now this data is way smoother. Everyone understood this? Now, how would you design an altitude control based on this? It's actually very simple. How would you design an altitude control based on this? Anyone? So here is what I'm going to do. Any ideas, online students? So, oh, graph here. Okay, actually, let's get the data. So what I'm going to do is, what would be a good place to do this experiment? I'm going to place it over here. Let's do the experiment. So in case if the students are wondering what I did, I placed the Mambo on a flat surface. And I'm going to see what is the value of altitude that I get from here. So moving average, this is altitude sonar. So I'm gonna click on here and I'm gonna run this code. So what happened? Need to fit this. Yeah, yeah. So this is the value that I'm getting. So which kind of tells me somewhere 0.44, 0.45. Clearly, this is not calibrated. So 0. Let's see what value do I have. Okay, still it is noisy. So what I'm going to do is I'm going to increase my moving average filter. And I think that is becoming noisy because when it speeds up, basically ultrasonic sensor vibrates, and that is actually causing some teeny tiny disturbances. Can you see that? So what I'm going to do is I'm going to do a heavy duty filtering and see how good the data is. So window length 100. Let's see. If MATLAB doesn't like it because it can't store 100 values at the same time, you see. So Tatvik, how would I, so here is what I want to do. I want the Mambo to go to a particular height and stay there. Okay. Everyone agrees with this idea? Okay, then what are your ideas? How would we make this happen? So what I want to do is I want it to go to a certain height. Now you'll see funny part. So it's still noisy, but it's not a lot. It's actually much better. Can you see it is between 4.3 and 4.3? So 4.3. So what I'm going to do is I want to design the controller and I want it to go to maybe say 0.5. Okay. So here is what I'm going to do. So I'm going to stop this. And I have to caution you again that the Mambo is going to crash, but don't blame me. So what I'm going to do is I'm going to go here, go to simulation. Why did it stop? Stop. Okay. Go to library browser, moving average, grab moving average here, get this from multitude sonar, take this out from here, remove this. Then in moving average, go to library browser, commonly used block, find the, so basically I want to find the difference. So basically subtract, so mathematical operations. Math operations. So you can do subtract, right. Actually, yeah, add, subtract. And then I will go to library browser, get a constant value. So we want to actually subtract this value. So I will do minus plus, and I'm going to add this. And what I want to do is I want to plot this. Or actually I can display this as well. So if you want to just display the value, that's fine too. So, but we can just plot it. And I'm gonna go to hardware, monitor and tune. And see what happens. Then go start. Double click. See what happens now. Now I'm gonna raise this. It go positive or it go negative? Negative. Huh? It went negative, right? Okay. So which means what I need to do is I flip my positives and negatives. Stop. Minus plus. And then whatever I have over here, I'm going to feed that to my motor mixing algorithm. Yeah, it's not going to be stable, however. It's going to be unstable, however. But oh, I didn't show you DC to PWM, right? No. I just showed you DC, right? No. Don't worry about it. So I think I just showed you this guy.
This won't work without proper power. Not proper power control.
I know it won't work without proper hover. That I know. So the only thing is I want to at least get you guys started. And I can promise you this, once you start playing with this, this is not difficult at all. This is not difficult at all. The only thing is you should start enjoying what you're doing and then start playing with it. So what was the difference? 500. So I'm gonna make it 1000. Tatvik, are you ready? Be careful. Be careful, okay? What happened? Oh, control subtract. To subtract. I didn't do subtract. I didn't save subtract. Apply. Okay. Okay. I think I will turn on my video. Okay, everyone, clearly it will be blurry. Correct. Okay, ready? I know. I don't know. We'll see. So now if I lift this, can you see it slowing down? Can you see? Actually, yeah, the online students can't see this. That's why you're missing all the fun. Don't. Why do you want to come here? You're not wearing safety glasses. Okay, come. Pull.
Okay.
Pull. And move it up and down. And tell me what happens in speed.
Oh. It's, yeah.
Anyone else wants to try?
Jesus. Can't just do whatever it wants.
No, man, because you are doing it too fast. Ah. Enlightenment.
I'm more intelligent now.
Because you took robotics too. Anyone else? Yeah, please. Yes, yes. Of course.
I need to test his theory.
You need to
I don't
test the
believe
theory.
it. I don't
Okay.
believe it.
Yeah.
I feel like it's a scam.
Yeah. Wait,
not-
let me start it.
Oh, I was like, it's not moving.
Correct. It's not moving because I haven't started it yet.
That could be the problem.
Stay away. Oh, hey, be careful, okay?
Oh no.
Move it up. So all my online students are missing all this fun. Mambo is flying. Who started this background music?
What is this like?
I feel powerful.
Okay, yeah, come. Now the black background is not blurry. Come on, show it to me. Okay, yeah, here.
It's powerful.
Yeah, see.
Oh.
Okay. Anyone else wants to try? Write that in my evaluation.
Got it. I'm doing that right now.
Yes. I go to robotics 2 class and I feel happier. Okay, Tatwik, go back. Be careful. I have batteries too. Maybe universe doesn't want us to do this experiment. So it took off, but it was not stable. Because why it was not stable? You don't have hover control. So first you need to implement the hover control, and then once you add this loop to it, you will actually be able to control it to whatever location you want. I don't know if online students saw this, but actually Mambo is smart. As soon as there is a flag set up, so as soon as there is a hit or something, the motors will stop. So can you see flight crash detected? So shutting down. That's why I like it. Yeah, so everyone saw the Mambo taking off. That is what you want to do. So God came off. Oh, oh yeah. I have non-zero yaw. It will give a problem. Will I crash it? Oh, you lost contact. Yeah, so this is the type of fun you can have once you have your Mambo working. And I'm gonna stop here. And if you have any questions, I would be happy to answer.
I don't know if it'll work with the Python. But I would check. Well, maybe it will work. Maybe it will. I have to test it on the phone.
Show me the block, the moving average block. Sorry, did you close?
I close it.
Oh no.
Professor,
Yeah,
first of all, I'm getting the logging error when I'm trying to
correct.
check
Because you are not using build, deploy, and start. You are using monitor and tune.
yeah,
You shouldn't use monitor and tune.
but for checking the ultrasound,
Yeah, but that will work. Just work on my computer, right? It should work.
also I think one of my motor is not working because
Which motor is not working?
this one.
I know, but you need to tell me the color.
I have the
How do I
red
tell
one.
the color?
You have to
How
take
would you see the color? You would see the color when you take that Mambo apart.
Can we have a red and black one?
Yeah, here is the red and black.
So much. And I take you don't have any white ones, right?
White ones are gone.
I think this is the one.
I mean, I can see a red and black there, so that's not
So, but you need the screwdriver to take it off. I can. So what you need to do is you need to take. Can you see that this? You have to take it off. You have to take the cover off.
Okay.
Then the whole thing will come off. Then you have to route the wire and replace it.
I should have the screwdriver. That's fine.
You have this screwdriver?
Yeah.
If you don't have it, yeah, I'll bring it back again on.
Okay.
What's the software? Software. Just Google Muse. Actually, if you look at the link, I have sent a lot of information on what Muse software to use. There's an SDK for Muse. Okay. Thanks, bro. Hover control assignment is due next week, next Tuesday.
For the first time I finished it on time.
Oh, you got hover control working? It actually hovers?
No, I didn't try it because one of the motor is not working.
got it working. We have a video.
I mean, I tried it like this and it was working, but I didn't.
Yeah, working like that is okay.
One of the motor is not working. So I
Yeah,
cannot
hover
make it
control will not work just based on P control. You will have to add the D. Without that, it will not work. So now the question is, how would you add D?
Next class.
Next.
Continue.
To be continued.
In the next episode of robotics 2.
Same block, you have successive differences. This block. So what you do is, whatever signal you are getting, you are gonna get the difference, and that is nothing but your input to D. And this will go to KD.
And that will be going to constant block half hour.
Yeah, and then what you will do is, whatever you have from your P, you add, there will be some block, and that will go to your.
Successive differences.
You're not done yet. Come on.
I don't know. I'm going to simulate.
So, how are you, Surya?
Great, Professor.
Okay, that's it for today. I will see you next class.